This is module 10.2, writing the equilibrium constant expression. Remember, K is the equilibrium constant. Make sure you are very clear that this is a capital K and not a little k. So consider the reaction AA plus BB goes to CC plus DD, where little a, little b, little c, little d are the coefficients. The equilibrium constant is going to be equal to the products over the reactants, all raised to their coefficients. I find it very useful to think of this as products over reactants, because one of the things we're going to be looking at is what does the value of K tell us about how likely a reaction is to go in the forward direction primarily. So what we're going to do is write equilibrium constant expressions for K, and then later we're going to be figuring out how do we put molarity values in for C, D, A, and B. So products on the top, reactants on the bottom. The stoichiometric coefficients are the exponents. So just to make really sure that you know what the coefficients are, those are the little baby letters, okay? So stoichiometric coefficients are the exponents. K depends on temperature, not concentration or catalyst. The concentrations are expressed in molarity or partial pressures if we're talking about gases. Only reactants or products with dilute concentrations that vary are included. This means that we omit, this is important, solids, immiscible liquids, or solvents. These are called heterogeneous systems. So we only want to use the things where the concentration changes, where we're starting with something that is dilute. So we're going to write some equilibrium expressions for some various equations. We're going to designate, when we're writing molarities, Kc. So Kc is for concentrations. So it's products over reactants. So we would write NO2 to the first, O2 to the first. Now, of course, you can leave the ones out. And then we have NO to the first, ozone to the first. Let's take a look at the one underneath it. So we have ammonia reacting with oxygen. In this case, we would write Kc is equal to NO2 raised to the fourth power, the concentration of H2O raised to the sixth power, the concentration of ammonia raised to the fourth power, and the concentration of oxygen raised to the seventh power. Now we're going to look at phosphorus reacting with oxygen gas. Notice that what we have is a solid here. So this is omitted from the equilibrium expression. So we would write that Kc is going to be equal, we're going to omit this one also, omit. Kc is going to be equal to 1 over the concentration of oxygen to the fifth power. So because we couldn't put anything to the top, we have that as a 1. So Kc equals 1 over oxygen to the fifth power. Let's take a look at the last one. Before we even start to write these, we look to see if there's anything we should omit. Yep, we're going to omit the sulfur. So let's write omit. So Kc is going to be equal to SO2, sulfur dioxide, raised to the 8th power, and oxygen molarity raised to the 2nd power. Now, a lot of times, if you're dealing with gas equilibria, your concentrations will be given to you in partial pressures instead of molarity. So this is designated Kp, P being for pressure rather than concentration. You write them just the same, except there's one very, very picky little thing. You have to use the designation for partial pressure. Otherwise, it's just the same. So let's consider the reaction of hydrogen with iodine to make HI. And this thing is completely in the gas phase. If the concentration was given to us in molarity, we would write HCl, well, not HCl, HI squared. Let's redo that. HI squared over H2 I2. However, if we are asked to write it in terms of partial pressure, we would need to write PHI squared over PH2 times PI2. Believe it or not, the AP grader will mark your answer as wrong if you do not use the correct form. So you must do this. So you must use the correct form or lose the point. So let's take a look again at what we did. When we write the equilibrium expression, we put the products over the reactants. We omit anything that is a solid or a liquid. And then if we are asked to write it in terms of partial pressures, we are going to use partial pressure symbolism rather than concentration symbolism. At this point, you're going to go to this link here, and there's some practice on writing equilibria expressions.